Hi, I'm Amashni. Welcome to Lesson 2 in the series of maths lessons on triangles. We'll kick off today's lesson by recapping some of your mathematical knowledge. Although there may be hundreds of different triangles, all triangles can be divided into three groups according to the information we have about the length of their sides. In this way, we get equilateral triangles, that is, triangles in which all the sides are equal. Isosceles triangles, that is, triangles in which two sides are equal. And lastly, scalene triangles. In scalene triangles, none of the sides are equal in length. There are also three categories that we can divide triangles into according to their angles. I'm sure you have seen this before. Triangles can be right-angled, that is where one of the angles is 90 degrees, or triangles can be acute-angled, that is where all of the angles are acute, in other words, smaller than 90 degrees. Or triangles can be obtuse-angled, that is where one of the angles in the triangle is obtuse or larger than 90 degrees. Now, for the rest of this lesson, as well as lessons 3 and 4, we'll be taking a closer look at the three triangles that we have defined according to their sides. You should already know that to organize and understand space, we have certain tools that we can use. These tools are defining, which means to talk and write words about objects, constructing, which means to make objects, and transforming, which means to change objects. We have already started to define triangles by naming them, and we will go into a bit more detail as the series progresses. Here is what we will learn today. By the end of this lesson, you should be able to define the scalene triangle, name three different types of scalene triangles, describe what is meant by the terms median, angle bisector, altitude, and perpendicular bisector. We will begin our investigation of different triangles by looking at the scalene triangle. I have already cut out a scalene triangle. Do you remember how I could confirm that this is a scalene triangle? That's right. A scalene triangle is defined as a triangle in which none of the sides is equal in length to any other side. So, to confirm that this is indeed a scalene triangle, all I would have to do is to measure the sides and to check that all the sides are of different lengths. I will start by labeling the sides of the scalene triangle. I will call this point A, B, and this one C. Let's measure the sides. So that confirms that we are working with a scalene triangle. Now, how can we find more geometrical properties in the scalene triangle? You should remember from our previous experience of analyzing geometric shapes that we could fold the triangle to find its line of symmetry. Do you remember what a line of symmetry is? A line of symmetry is a line that divides a shape or an image into two identical parts. The scalene triangle has none of the sides equal in length. Do you think this would affect symmetry in the triangle? Here's my scalene triangle. I want to see if I can fold the one side onto the other. Can you see that no matter how hard I try, we cannot find a line of symmetry in the scalene triangle? So we see in the scalene triangle, none of the lengths are equal, and we therefore have no lines of symmetry. What else can we do or construct in the scalene triangle? Let's have a look. Here I have a diagram of two scalene triangles. I've already labeled them A, B, C and D, E, F. We'll begin this exercise by working with triangle DEF first. Do you remember that we said, what else could we do to this triangle? we could actually bisect the angles. Do you remember that to bisect means to cut into two equal parts? Why don't we construct a line to do this? To bisect the angle, I will use a pair of compasses. We can choose to bisect any one of the three angles in the triangle. I choose in this instance to bisect angle E. We place the compass point on the vertex E. I draw an arc that cuts side DE as well as FE. I now place the compass point at the point where the arc intersects with side DE, and I draw another arc. I do the same by placing the compass point on line FE, where the arc intersects with it. I draw another arc. We see that we end up with two arcs intersecting. If I had to draw a line through the vertex E and this point which we have just constructed here, this would be our angle bisector. I'm using a Koki so that you can see the actual line. This point at angle E is now equal to this point. So angle E has been bisected. This line that we have just constructed has a special mathematical name. It is called an angle bisector. Here is its definition. Angle bisector, the line that bisects an angle in a triangle. I have constructed the angle bisectors in triangles ABC as well as DEF. Let's have a look at our graphics again. Because we have drawn in all the angle bisectors, I have marked the equal parts with the same symbols. Now, do you notice anything interesting? Right, these lines pass through one point, here. And in this triangle, they also pass through the one point, here. This point has a specific name. Point of concurrency. The point of concurrency is where two or more line segments, rays, and even planes intersect in a single point. Let's take a new graphic of our two scalene triangles and see if we can construct any other lines. In our previous triangle, we bisected the angles. Can you think of anything else in this triangle that we can divide into two equal parts? What about the sides of the triangle? Let's use our pair of compasses to find the midpoint of line segment AC. I start off by placing my compass point at A. I draw an arc. I then place my compass point at C and draw another arc. I will now construct a line that passes through the points where these two arcs intersect. Remember, this line will be passing through the midpoint of line AC, which is here. I will mark this midpoint, point M. Using the edge of a set square, we can see that there are many lines that can pass through midpoint M. We could, for example, draw the line that is perpendicular to AC. We see with the edge of the set square that this is a 90-degree angle. Let's use our ruler and now construct a line that is drawn from the vertex B passing through midpoint M. Okay. Each of these lines that we have just constructed through the midpoint has a specific property that makes it special. When we go back to our diagram, we will describe these properties a little more mathematically. The first line we said passes through the midpoint of line segment AC. We use the edges of a set square to prove that this is indeed 90 degrees. We say that this line is perpendicular to AC. Now, because this line also passes through the midpoint of AC, we call this line the perpendicular bisector. Perpendicular bisector is a line that bisects a line segment at a 90-degree angle. The second line that we constructed passes through point B and the midpoint of line segment AC. We call this point B a vertex. A vertex is a very special point in geometrical shape, and it is usually a place where two or more lines or edges meet. Line BM is called a median. Median, a line from the vertex of a triangle to the midpoint of the opposite side. Now you see that the triangle has three vertices and therefore has three medians. Now imagine if I had to draw the other two medians in. What do you expect? Here you can see that in triangle ABC, the medians are concurrent. Remember that this means that these lines pass through one point. If we construct all the perpendicular bisectors in triangle DEF, we can see that these lines are also concurrent at this point here. For this next construction, I would like to do things a little differently. I'm going to first give you the definition of the line. This definition might be familiar to you because you have worked with this before. This line is called the altitude or perpendicular height of the triangle. The definition for an altitude is a line segment from the vertex of a triangle perpendicular to the opposite side or to the line containing the opposite side. The interesting thing about altitudes in certain triangles is that their construction is very unusual. Have a look at this. Can you see that in order for me to construct the altitudes in this triangle, I had to produce side CA to this point and side BA to this point. And the points where the altitudes intersect is on the outside of the triangle at point U. Here, in this triangle, we have constructed altitudes, or in other words, lines that pass from the vertex perpendicular to the opposite side. And we see here that the altitudes intersect on the inside of the triangle. So now what is it that makes triangle ABC different from triangle DEF? Here is a clue. Have a look at the size of their angles. Can you remember how we name triangles according to their angles? Triangles can be right angled, or they can be acute angled, or the triangles can be obtuse angled. We can use this information to help define our scalene triangles in a little bit more detail. Triangle ABC that we use in our constructions can thus be called obtuse angled scalene triangle, and triangle DEF that we used in our construction could be called acute angled scalene triangle. Now, do you think we could get a right angled scalene triangle? Look at this example. If we measure the sides using a divider, we see that the sides are obviously not equal to each other. Now let's measure the angles using a protractor. And we see, yes, indeed, it is 90 degrees. We can now say that this triangle PQR is a right-angled scalene triangle. We have discovered a lot of new interesting terms while analyzing our scalene triangles. Let's recap what we have learned. We learned that we can construct the following lines in a scalene triangle. Angle bisector, the line that bisects an angle of a triangle. Perpendicular bisector, the line that bisects a line segment at a 90-degree angle. Median, a line from the vertex of a triangle to the midpoint of the opposite side. Altitude, a line segment from the vertex of a triangle perpendicular to the opposite side or the line containing the opposite side. Thank you for joining me in this lesson. I hope to see you in our next lesson where we examine the isosceles triangle. Bye.